Questions about anything from last time? Or anything? There's been some questions on Piazza about branches of square roots, which I've responded to now. So if you're thinking about that kind of thing, you might check that out. Let's see. So last time at the end of the hour, I was working on showing this fact that if you've got an analytic function on a domain, then it has an analytic antiderivative if and only if the complex contour integral of f around every closed contour in that domain is 0. So this is a hypothesis that for all closed curves gamma in omega. Okay, and last time I showed you that this direction of the implication, that if it has an analytic antiderivative, then you write out those integrals and you're integrating f prime around a closed contour. And when you use the fundamental theorem of calculus for complex integrals, you see that that's got to be 0, because that would be f at the end minus f at the start, and the end and the start are the same, capital F, that is. So last time I showed that's easy, and in going the other way, so then we assume that the integral around every closed contour is 0, and that allowed me to show you that we define a capital F of z to be the integral along a curve that starts at a fixed point A and goes to z of f of w dw. And last time we showed that that's well defined. And it's the hypothesis that allows me to see that that's well defined. So last time we checked that capital F is well defined, meaning it doesn't depend on the curve. I could pick any curve that starts at the fixed point A and goes to the point Z. Okay, so today, to finish up, I need to show that f prime is equal to little f. Whenever z is a point in omega. Okay. And this is a sneaky little trick that we'll use multiple times. Since this thing doesn't depend on the curve, it allows me to do this. So here's my omega. It's a blob. It could have a hole. And let's say I want to show that this thing is differentiable at a point Z. Or let's make it near a point, here's A, and let's make it near a point Z naught. And so I want to calculate a complex difference quotient in this little purple circle here. Let's make a little circle about this Z naught. And I want to take a difference quotient about this point Z naught. Here's a Z. And the radius of this thing, let's call this radius little r. Okay, so I want to calculate a difference quotient about that Z naught point. And because it's an open set, I can stick a disk in like that. So omega is open. So there exists a disk of radius r about any point I pick, z naught, that's contained in omega. And that r would be positive. Okay. So now here's what I'm going to do. To think about the difference quotient, I'm going to take my curve gamma to start at A and go to z naught. So just pick one. But then when that's going to go A to z naught. But then when I want to go from the rest of the way to z, I'm going to take the straight line. So I'll take this z naught to be here. Where do I want? I'll take z here. I'm going to take a straight line going from, let's see, this is a straight line. So I'll make that blue line there is L, the line that starts at z naught and goes to z. And of course there'd be an arrow on it going like that. Okay, and so I'm going to take the difference quotient here. The difference quotient, that would be f of z minus f of z naught over z minus z naught. Okay, and that's going to be 1 over z minus z naught. F of z is the integral. It's going to be the integral from a to z naught, followed by the integral along the straight line from z naught to z. Because it's independent of path, I can take that path of f dw, and of course f of z naught is the integral from a to z naught. Those are going to cancel out. So this integral cancels with this integral, and I'm left with something rather simple, and it's kind of like when you look at the proof of the fundamental theorem of calculus in your freshman calculus book. That means we're actually integrating along something really small, a small segment. And so we get an integral along a little tiny segment times f of w dw. And now the question is how we're going to analyze that. I expect this limit to tend to f of z naught. And so because f is, notice that f analytic at z naught, near z naught, implies that it's continuous. We know that fact. So I kind of want to show that that limit goes to f of z naught. That means that f of w is equal to f of z naught plus an error. And because of continuity, that error goes to 0, where E of w tends to 0 as w tends to z naught. Okay, so now here's what I'm going to do. That difference quotient, there it is at the top there. The difference quotient is 1 over z minus z naught. And then I would have the integral along the line segment, z naught to z, of a constant. This is a constant thing. Plus my error Okay. And that constant thing I can integrate because that is the derivative of something. That's equal to d by dz of constant times z. And so I can use the fundamental theorem of calculus to calculate that first integral. And so what I get in that, I would get 1 over z minus z naught. And then for that first integral, I would get f of z naught. Let's see, it's actually times w. F of z naught times w evaluated between w equals z naught and w equals z, which is going to give me a z minus z naught there, plus something I hope is going to be small. It's going to be an integral along a really small path times a really small function. So that's going to be so small that even when I divide by 1 over z minus z naught, it still goes to 0. So this thing right here, by the fundamental theorem of calculus, is f of z naught times z minus z naught. And so here's my difference quotient. Those cancel. That's fantastic. That's exactly what I needed. And so I get what I expect the limit to be, plus something that's presumably really small. So I would call this the error. Why don't I call it curly E? It's going to depend on z. So I'll call it curly E of z. And now all I'm going to do is use the fundamental basic estimate for integrals to estimate that thing. So and now we estimate curly E of z. Let's see, that's going to be less than or equal to, I'll have a 1 over z minus z naught modulus here that just goes along. But then I'm going to use the basic estimate for integrals. That would be the max of the modulus of E of w when w is in the little line segment there, times the length of the little line segment. And the length of the little line segment is just the modulus of z minus z naught. And that's fantastic. That cancels the nasty thing in front there. And then I have the max of a function that goes to 0 on that little line segment. And this goes to 0. This goes to 0 as z tends to z naught by continuity. Because e to the w goes to 0 as z tends to z naught. And so that's the proof. And it's very much like if you looked at a very careful proof of the fundamental theorem of calculus, it's exactly like that. So it's kind of amazing that in this context where these symbols mean something totally different, it's the same idea and it works great. Questions about that? Done. So I cooked up an analytic antiderivative. Okay, now kind of a drum roll, because now this is going to bring us to a big moment in the class where we get to Cauchy's theorem and Cauchy's integral formula. The subject kind of explodes after this event because these things have so many consequences, strong consequences. And that's why people back then got so excited about this subject. Here's a very simple picture and way of thinking about, there's lots of versions of Cauchy's theorem. The simplest one I like is, suppose F is analytic. I'm going to use a new term here. Inside and on a simple closed curve. Sometimes those are called Jordan curves. A simple closed curve gamma. Some word for that is a Jordan curve. I'll explain what I mean by inside and on. Then the conclusion is that the integral around gamma of the analytic function f dz is 0. Okay, the picture here is a simple closed curve never crosses itself. And the Jordan, famous mathematician who studied them, showed that a simple closed curve has an inside and an outside. So here's my simple closed curve, gamma. Okay, now by inside and on, I mean it's analytic in a neighborhood, an open set containing that simple closed curve. And not only that, it's analytic all the way through to the inside. And it's rather a subtle question how you know a Jordan curve has an inside. And that was the Jordan curve theorem. A simple closed curve splits the plane into two pieces, an inside and the outside. Draw a picture, everybody believes that. But the Jordan curve turns out to be a rather challenging thing to demonstrate. And so we won't dwell on that. The curves we draw, like that one, you say, oh yeah, I see the inside and I see the outside. So we're not going to get bogged down in thinking about the Jordan curve theorem. Anyway, I'm assuming there's this open set about gamma, where f is analytic. And not only that, but it extends to be analytic through the inside of that curve. So the picture would look like this. So f is analytic on that shaded region. On this shaded region. Okay, that's the assumption. And so what is that? That's an open set containing the curve and the inside of gamma. I'm going to demonstrate this carefully in the case of a disk where you don't have to think about any of these more subtle questions about Jordan curves. Because just knowing this fact in the case of a disk is going to give us gobs and gobs of important things about analytic functions. Okay. That's the picture. And the key here is going to be two things: Green's theorem and the Cauchy-Riemann equations. Green's theorem and Cauchy-Riemann, and combining the Cauchy-Riemann equations. That's going to be all there is to it. Okay, so let me tell you what Green's theorem is. I like to write Green's theorem in green. In that picture, it's a statement about line integrals. Integral around gamma of p dx plus q dy equals an area with respect to area, an integral with respect to area over the inside of that curve. So that's the omega here of dq dx minus dp dy. In the case of a disk, this is a very elementary theorem just involving the fundamental theorem of calculus. Okay, this is gamma is a simple curve, simple closed, and omega is the inside of gamma. And this dx dy is the element of area, dA. Okay, first of all, let me review something. You know what an area integral is. You may be rusty on your Math 261. The integral along gamma of p dx plus q dy is notation for the integral from a to b, where we parameterize the curve, of p of x of t, y of t. Those are parameters for the curve. Dx is shorthand for dx dt dt. That's what we think of as the dx standing for. And then, of course, the q one is integral from a to b of q of x of t, y of t. And that dy is shorthand for y dot of t dt. Okay. That's just a quick review of what those symbols mean in Math 261. So now we can proof of Cauchy's theorem. Let's calculate, using our standard notation, f of x plus iy is u of xy plus iv of xy. So remember in Math 425, F analytic. What? F is analytic means U and V are C1 smooth. When you do greens, you need that. U and V are C1 smooth and satisfy the Cauchy-Riemann equations. Remember what those are. Du dx equals dv dy, and du dy equals minus dv dx. Those are the Cauchy-Riemann equations. Okay, so this means we're good for greens. You need that kind of hypothesis to make sense out of those integrals and to do the proof. So our gamma is parametrized by z of t equals x of t plus iy of t. And remember what the complex integral stands for. Integral along gamma, let's see, as t goes from little a to little b. Integral along gamma of f dz is shorthand notation for a real integral. Let's see, an integral from a to b of f of z of t times z prime of t dt. Let's see, I'll write it out in gory detail and then I'll start simplifying the notation. So that would be integral from a to b of u of x of t, y of t, plus I v of x of t, y of t, plugging it in, times z prime of t, which is x dot of t plus I y dot of t. And remember, this symbol, this kind of integral means split that junk into real and imaginary parts and do the real and imaginary integrals. And so that's what I'm going to do now. And now I'm going to snap it up a little bit and write it out more quickly. Let's see, that will be the integral from a to b. The real part's going to be, let's see, I get a u times an x dot. U times x dot. I'll get an I times an I. That'll be real. That'll be v minus v times the y dot. That's starting to look like a Green's theorem thing. Plus, then we'll get some imaginary stuff. Integral from a to b. Let's see, imaginary would be u times y dot plus v times x dot. Okay. And in the notation of Green's theorem, that stands for the integral along gamma of, let's see, this one is u dx minus v dy. And this one is I times, this one is the integral along gamma of u dy minus v dx. And it turns out when you use Green's theorem for those, those are going to give me two of the Cauchy-Riemann equations, which are going to be zero because of that. So I probably screwed up there. Yeah, it's plus. That made me feel strange, too, because I realized they're not usually the same like that. Thanks. Okay, so now right here is by Green's theorem. Let's see, I'm going to use Green's. What is, remember it was p dx plus q dy. So this one is p is going to be equal to u. But here I've got to take a q is equal to minus v. And let's see, this one, this v is, it's p dx. So the v is going to be the p here. And u dy is going to be the q. Okay, so when I use Green's theorem, let's see, it's dq dy. It's going to be an integral over the inside of, let's see, the q dy, that would be d by dy of the q is minus v minus d by dx of u. The area. Plus I times integral around over the inside. Let's see, dq, this one would be d by dy of u minus d by dx of p, which is v, the area. And sure enough, I see the Cauchy-Riemann equations. What is this? I get minus dv dy minus du dx. Du dx is equal to dv dy. What? Am I screwing this up? V is minus. minus dp dx.
Is it plus ddx of u?
What?
Is it plus ddx of u on the left?
I think the Green's theorem was dq dx minus dp dy.
Oh, for crying out loud, did I really do that? Did I screw up Green's theorem above? Yeah. You know how I remember Green's theorem? I derive it from Stokes' theorem every time I use it. So, obviously, when I don't do that, I forget it. Right. So, it's dq dx minus dp dy. dq dx minus dp dy. And I took different q's and p's in each one of these things. Anyway, now this is more like it. This is dv dx. And these, yeah, so that's going to be a big fat 0 by Cauchy-Riemann equation number 2. And this one's going to be du dx minus dv dy, and that's identically 0. This is Cauchy-Riemann equation number 1, and this is Cauchy-Riemann equation number 2. And so we get a big fat 0 here, and that's the Cauchy theorem. So it's just a write-down using Green's theorem and the definition of all these integrals and the symbols they mean. Questions about that? Okay, so that's the content of section 4.4b. Okay, did I call that Cauchy theorem number 1? No, because now I'm going to do Cauchy theorem number 2. Questions about that? So here's Cauchy theorem number 2, which is, in some books it's written like this. Cauchy theorem number 2, it's really the same thing, but suppose, notice the inside of that curve gamma didn't have any holes. That is always the case. So suppose omega is a domain with no holes. Okay, that's not a very mathematical term. But in the mathematics, there's this fancy thing that says that this is a simply connected domain. That's the fancy word for no holes. I guess I might as well say what that means in mathematical sense. Every closed curve in omega can be squeezed down to a point continuously. Every closed curve in omega can be deformed. Think of it like a rubber band, and then you start shrinking the rubber band until it shrinks down to a point. Every closed curve can be deformed continuously. In omega, can't leave omega, down to a point. That's the mathematical, that's called homotopy. You take a curve and you continuously deform it. And you can squish it down until it gets smaller and smaller until, boop, it just is a point. Okay. And we're going to suppose F is a domain. And suppose F is analytic on on that omega. Then the conclusion of Cauchy theorem number 2 is that the integral around any closed contour is 0. Then the integral around gamma of f dz is equal to 0 for any closed curve in omega. Got to be closed. So, as a consequence of the thing we started out with, that means that on a simply connected domain, all analytic functions have analytic antiderivatives. So, analytic functions have analytic antiderivatives. On simply connected domains. By the previous result. Okay, I'm not going to dwell on a proof of this one. I gave you the big one of the day is the Green's theorem thing. But the y here is I got a simply connected domain, so there's no holes allowed now. Notice it kind of looks just like a simple closed curve. That's the feeling for a simply connected domain, the inside of something. If I have a closed curve in here, just draw a couple. It could cross itself. So here's one. I'll make it a figure 8. I could split this simple closed curve gamma into loops. And those integrals around those loops would be 0 by Cauchy number 1. So cut up closed gamma into smaller loops. Cut up closed gamma into loops and use Cauchy number 1. That's the feeling. So this is the feeling proof. I'm not going to dwell on a mathematical rigorous proof at this point, just because it's not really going to be worth it for us. Because in the case of the disk, it's going to be a very clear, obvious thing. And that's the one I'm going to dwell on. Questions about that? Yeah.
I'm a little confused. Like, you're saying you're shrinking it down to a point, but then it's no longer closed. Like, there's nothing inside, right?
Right. The curves get smaller and smaller, and the integrals along those little curves would go, and the limit would be the integral along a point, which is 0.
Okay, but then it's no longer a closed curve.
That's true. That's why I said it goes boop, gone,
Okay.
at the end.
Okay.
Yeah, so that's... So if you think about why that's a reasonable definition, if a domain had a hole, you'd make a curve go around it, and think of it as a rubber band. You'd start shrinking the rubber band, and it would get stuck on that hole. So that is the obstruction to that homotopy thing.
So that's why the domain can have holes in this case.
Right.
Okay.
Let's see. Did enough technical things for today. So the exciting next step.
What if the hole is also a point?
That would be a problem, because then when I do my homotopy, it would go down to that point, and it wouldn't be in the domain. So
Okay.
yeah, a point is a hole. In fact, if you start trying to do a Cauchy theorem for 1 over z on the punctured plane, you'll see that there's no Cauchy theorem for 1 over z. The integral around a closed thing, around a circle about the origin is going to not be 0. In fact, that's the next step. It's going to be an exciting next step is the Cauchy theorem is going to imply the Cauchy integral theorem. So that's a famous thing called the Cauchy integral formula. And here's the picture of a Cauchy integral formula. I would have a closed contour, a simple closed curve like this, gamma. And I have a point. Let's see, once again, my f is going to be analytic inside and on. Okay, and I have a point A inside that thing. So the assumptions are f is analytic on an inside and on. Gamma is going to be a simple closed curve. A is going to be inside gamma. And then the Cauchy integral formula is going to say the value of the analytic function at A is an integral. And it's a 1 over 2 pi I integral around gamma of f of z over z minus A. The Cauchy theorem doesn't apply here because 1 over z minus a has a bad spot at a. So that function inside there is not analytic inside and on. Something terrible happens at a probably, where it would blow up. So the Cauchy theorem doesn't tell you that's going to be 0. The mind-blowing thing is that's equal to f of a. This is my favorite formula. If I was ever going to get a tattoo, that's the one I would get. I haven't decided where exactly, but yeah.
So this is part of the residue theorem? I just see.
Yes, you could think of this as a simple case of the residue theorem.
Oh,
The residue of that function inside the integral is going to be f of a. Right. The residue theorem is a fancier version of the Cauchy integral formula. But here's why this is a mind-blowing thing. It means that if we know of analytic function on the curve, it's completely determined inside. So that's pretty weird because, you know, differentiable functions, there's lots of them, and you can mush them around. You can change their values in the inside without changing them on the curve, just by pushing and pulling it. Think of it deforming it by just pushing the graph with your thumb. You can't do that with analytic functions. They're sort of rigid. If you know them on the green curve gamma, they're completely determined all the way inside. So that's a very strong property. It kind of means that there's lots of analytic functions, but this means that they're not as many as you might have thought. They include polynomials. They include a lot more than polynomials, but they're rigid. You can't push them around. Before we do it for this general case, I need to do an important calculation on a disk to get ready for next time. Let's take a disk, a circle, of radius, let me take the center here. Let's take the radius to be r. So this is going to be a circle. I'll call this circle CR of A. that's going to be parametrized by z of t equals a plus r e to the it as t goes from 0 to 2 pi. I'm sorry. Well, the important calculation is if I take a w in here, I'll take a z naught. I'll call this z naught. Then the important calculation is the 1 over the integral around the circle of radius r about a of z minus z naught dz is equal to 2 pi I. That's where the 2 pi I in the Cauchy integral formula is going to come from. It's 2 pi I if z naught is inside that circle. And it's 0 if z naught is outside. Of course, that's the Cauchy theorem. By Cauchy's theorem. Because then that thing would be analytic inside and on the circle, and so the Cauchy's theorem would say that that's got to be 0. But of course, when z naught's inside, that hypothesis is not met. It has a nasty blow up at z naught. Okay. And there's multiple ways to do this. I think the most straightforward way is to use a branch of log. So I'm going to take a branch cut. I might as well use the principal branch. When I take the principal branch of log, I'll have a branch cut that goes out like this. That's going to be a branch cut for the principal branch of log of z minus z naught.
So what is z naught in this case?
It's just a point inside that circle, any old point. It's fixed.
It's not a hole though.
No, it's a point. But you may think of it as a hole. F is analytic on the whole inside except that point.
Yeah.
So it's a hole in that sense. That means the function 1 over z minus z naught. So it's kind of a hole for that. So I can't use Cauchy's theorem because of that. Okay, so this integral is going to be by the fundamental. Let's see, I'm going to go. There's in my picture. I guess I should copy. I'm going to run out of time. Maybe I'll just sketch this and then do it carefully next time. I'm going to start my curve instead of doing it from 0. I'm going to start right here. So let's call this A sub epsilon, and this B sub epsilon. And I'm going to let those epsilons slide into that. I'm going to let this one slide up, and this one slide down to the cut. And so I can calculate this thing as the integral of d by dz of the principal branch of log. Let's see, I'm going to take a limit. D by dz of the principal branch of log of z minus z naught dz, and I'm going to take a limit here as epsilon, A epsilon goes up and B epsilon goes down. Okay. And so by the fundamental theorem of calculus, that's going to be equal to log of z minus z naught evaluated between the starting point to the end point. And I'm going to show you that that's going to be 2 pi I.